Hey guys. Last time we were talking about impulse and momentum, and we used the impulse momentum theorem for some really simple problems. And right now, I want to use the impulse and momentum theorem for a slightly less trivial problem. So, what I want to do is to imagine that we had a baseball bat. I know there's several baseball players on the team or in the course. So what we will do is we'll have a person swinging a baseball bat, and the problem I have, I pulled out of a textbook. They give the initial and final velocity of the ball, and then you can work backwards to find the impulse on the bat, and then from that you can find the average force on the bat, and you kind of get a feel for how many newtons of force there are when you hit something. Okay, so I'm going to borrow numbers here from this example. I don't normally like to do that, but I will here. First off, so the scenario is the following. We have a bat hitting a ball. The ball starts out going in, and it returns going the other way. So V initial will be in this direction, and V final will be going the other direction. Okay, so the ball will have a mass of 140 grams. So I'm going to assume the mass of the ball is 140 grams. And we're going to assume that when the ball is flying through the air, it initially has a speed of 39 meters per second. And we're going to assume that after it leaves the bat, it also has 39 meters per second, but in the opposite direction. Okay, so we'll assume that V initial is 39 meters per second. But it's initially, the way I drew it, initially it would be to the left. So I want to say that's a negative 39 meters per second. And V final would be to the right, and we're going to say it's a positive 39 meters per second. Okay? So watch the minus signs on these things. These are vectors. They have all the rights and privileges thereof. All right. So we have the initial and final velocities. We have the mass of the ball. That means we can calculate the change in momentum. And then using the impulse momentum theorem, we're going to be able to deduce the impulse on the ball. Okay, so how do I do this? Well, what's my general strategy for applying a conservation law? I define the system. Well, I have information about the ball. So I probably ought to make the ball be my system. So the system will be the ball. And then the next step is to write down the impulse momentum theorem. So system equals ball. And then I write down delta P equals J. Well, okay, so now I just use arithmetic. So the mass, change in momentum equals the mass times the change in velocity. So that is going to be, so that's equal to the impulse. So that's going to be 0.14 kilograms times the change in velocity. Now, if you're really glib or you're not careful, you'd say, oh, it's 0. Not right. Final velocity is positive 39. Initial velocity is negative 39. Final minus initial is 39 minus negative 39. So that's going to be 78 meters per second. 78 meters per second. And if you're doing the arithmetic, which you all should be doing, we learned that is 10.9 kilogram meters per second. That's the impulse, J, on the ball coming from the bat. Okay? So that's pretty good. So that gives us the impulse. But you know, if I want to think about this, or get some sort of an intuitive feel for it, I don't want to think about impulse because, you know, before today, who the hell heard of impulse? Instead, let's work with forces. And to do that, I'm going to use the fact that the impulse equaled the area under the force time graph, or it's equal to the average force times the time interval. So it turns out, according to our infallible textbook here, that the average or typical time for a collision is 1.2 milliseconds. So I'm going to go and write that down over here. Delta T for the collision is 1.2 milliseconds. So if I know the impulse equals 10.9 kilogram meters per second, I know then, but I also know that the average force times delta T equals J. I can rearrange that to say that the average force equals J, 10.9 kilogram meters per second, divided by delta T, which is 1.2 seconds. And if you're going through the units, you can see that they cancel out. And the final answer that we get is 9080 newtons. Holy crap. Remember, when we killed the person on the roller coaster, we were talking about 5,000 newtons. Well, yeah, well, I guess it makes sense too. If you hit someone with a baseball bat, they're probably going to die. Anyway, aside from that, even if, bad example, sorry. I guess it's just good that you should feel good that it worked out the way it probably would have in real life. All right. Okay. Yeah. All right. Let's leave it at that.